In this video, we'll define torque and the equations that we can use to calculate it. Just like forces can affect the linear motion of an object, torque can affect angular or rotational motion of an object. For example, if you want to tighten or loosen the nut on a bolt, you might use a wrench to apply a torque to twist the nut like this. As you can see, we usually use a script T or Greek tau to represent torque. Or another example is to apply a torque to the lid of a jar to close it, or to turn a screw with a screwdriver, or to open a door. You can think of torque as the angular equivalent of force, and just like Newton's second law describes how net force causes linear acceleration, we'll see in a later video that there is an angular equivalent of Newton's second law that describes how net torque causes angular acceleration. But torques are actually produced by forces. For instance, the torque shown here on the door might be created by a force applied like this, or the torque on the wrench might be created by applying a force like this, or the torque on the jar lid might be created by a series of forces everywhere your hand touches the lid. As an example, here are 4 possible forces that may be creating this torque. The amount of torque that is produced by each force depends on how the force is applied. To explain this, let's again consider the wrench being used to tighten a nut. From your own experience, you may know that you can apply more torque to the nut if you apply the force closer to the end of the handle. So a force applied here, let's call it force 1, creates more torque than force 2 of the same magnitude applied here. And the angle of the force also matters, so force 3 of the same magnitude applied at an angle like this creates less torque than force 1. As we'll see shortly, force 1 and force 2 are actually applied at the optimal angle to create the greatest torque. And finally, the magnitude of the force matters. So if the magnitude of any one of these forces is increased, then the torque associated with that force increases. All of these factors are captured by an equation to calculate the torque produced by a force. There are several versions of this equation. Here's the first version that we'll discuss. Torque about rotation axis A is the magnitude of r times F perpendicular. R in the equation is the displacement vector from the rotation axis to where the force is applied. F is the applied force that creates the torque. And F perpendicular, the last variable in the equation, is the component of the force that is perpendicular to the direction of the r vector. Let's look at the wrench example again to visualize these variables. If the force is applied here, and the rotation axis, which is the center of the rotation, is here, then that creates a torque around the rotation axis like this. And the r vector, which by definition runs from the rotation axis to the location where the force is applied, is then here. And the greater r is in the equation, the greater the torque is, which is consistent with what we said earlier about the placement of the force. The other variable is the component of the force that is perpendicular to the direction of the r vector, and that would be here. And just to clarify, here's the component of the force that is parallel to the r vector. And we can also add the angle between the r vector and the force vector, which is here, and then using trig, we can see that F perpendicular equals F times sine theta. Using that relationship, we can then replace F perpendicular in the original torque equation with F sine theta, and the torque equation can be rewritten like this, where theta, again, is the angle between the r vector and the force vector. We can come up with one more iteration of the torque equation by going back to the diagram, and this time drawing components of the r vector that are perpendicular to and parallel to the force vector. To make it easier to visualize, I'll add lines that are perpendicular to and parallel to the force vector. Given that, here are the components of the r vector that are perpendicular to and parallel to the force vector. Just to clean up the figure a bit, I'll now remove the perpendicular and parallel lines. Because of the geometry, we can see that this is also theta, so r perpendicular is equal to r times sine theta. Now looking back at our torque equation, here is r times sine theta, so we can replace that with r perpendicular, and the equation becomes this, where r perpendicular is the component of the r vector that is perpendicular to the direction of the force vector. R perpendicular is often used when calculating torque, and it's commonly referred to as the lever arm. And now we have the three variations of the torque equation. Of course, all three variations are just mathematical variations of the same equation, so we simply use the one that is the most convenient given the information that's available to us. Two other details that I'll add to this description of torque are the SI units for torque, which can be seen from the equation, are newtons times meters, and by convention, counterclockwise is the positive direction of torque and clockwise is the negative direction of torque, though these signs may be defined differently, just as coordinate schemes may be defined in different ways. Note that the equation doesn't produce the sign of the torque. You will need to look at the figure to determine if the direction of torque is clockwise or counterclockwise. Here's an example to demonstrate the use of the torque equation. A mechanic tightens a nut with a wrench. He holds the wrench 15 centimeters from the center of the nut and presses down with a force of 40 newtons at the angle shown. What is the torque caused by this force about the center of the hex nut? Given the direction that the force is applied, the associated torque around the center of the nut will be clockwise like this. So when we calculate the torque with the equation in a moment, we will put a negative on it to indicate that the torque is clockwise. I'll do the calculation with all three versions of the torque equation to demonstrate how each is used. Let's start with this version. The R vector in the figure is here, and we're told that the distance from the rotation axis to where the force is applied is 15 centimeters, so the magnitude of the R vector is also 15 centimeters. The angle theta in the equation is the angle between the R vector and the force vector. The easiest way to visualize the angle between two vectors is to put the tail of the two vectors together, so I'll redraw the R vector here, and then we can see that the angle between them is 150 degrees. Now let's plug all these values into the equation, where I've added the negative sign because the torque is clockwise, and the answer is -3 Newton meters. Now let's try this form of the equation. This form uses R perpendicular. To visualize where R perpendicular is in the figure, I'll extend the force vector a little like this, and then I'll draw the component of the R vector that is perpendicular to that line. Applying trigonometry, we can then see that R perpendicular is R times the sine of 30 degrees. And so substituting that in and plugging in values, we get the same answer we did before. And then we can use the last version of the torque equation, which includes F perpendicular. Here are F perpendicular and F parallel in the figure. And with trig again, we can see that F perpendicular is F times the sine of 30 degrees. And substituting that in, we get this, and then plugging in values, we of course get the same answer we got the previous two times. The last thing I would like to discuss is calculating the net or total torque. Net torque is simply the summation of individual torque values. So in this equation, T1 is the torque due to force 1, T2 is the torque due to force 2, and so on. Torque is not a vector, at least not the way we apply it in this class, so adding up individual torques is pretty straightforward, but do remember that they're signed, so be sure to apply the signs for each torque. The net torque may also be calculated by using the net force in any of the previously discussed versions of the torque equation, like this. The R vector then is the displacement vector from the rotation axis to where the net force is effectively applied, and theta is the angle between the R vector and the net force vector. And so that's the introduction to torque. We will apply torque to more situations in the next video.